Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today I want to go over an example of circular motion and a rotational motion combined. So a sphere of mass m and radius r is released from rest at the top of a curved track of height h. The sphere travels down a curved track and around a loop of radius r. The sphere rolls without slipping during the entire motion. Point A on the loop is at height r, and point B is at the top of the loop. The rotation of inertia of the sphere is 2/5 mr squared. Express all your answers in part A through D in terms of m, r, h, capital R, and physical constants as appropriate. Assume lowercase r is so much smaller than the capital case R. So the dimension of the sphere is so much smaller than the dimension of the hoop. So part A, on the dots below, which represents the sphere, draw and label the forces, not components, that exerts on the sphere at point A and at point B, respectively. Each force must be represented by distinct arrows starting on and pointing away from the dot. So at sphere A, we know there is definitely gravity, which is pointing downward. We know the track is pushing the sphere inward. That's N, that's called the normal force. Here is the friction force. Many people make a mistake on friction force because at that point the sphere is going up, so logically a lot of people think friction should be down. But think about it, the sphere actually is rolling, it's not sliding. So the friction is to slow down the rolling. To slow down the rolling, the friction has to be upward. The friction is up because it slowed down the rotation. Next one, at part B, in this case, both forces are downward. Both gravity and the normal force are down because the track is pushing the sphere inward. So make sure you label 1. Derive an expression for the speed of the sphere at point A. So we can use conservation of energy. So if we decide at A that energy is 0, then the potential energy at the highest point would be mg times h minus r. And at A, because the sphere is rolling and it's moving translationally, linearly, so you'll have 2 kinetic energy. The potential energy at the top of the track, mg times h minus r, equals to translational kinetic plus rotational kinetic. We know I equals to 2/5 mr squared. We know omega equals v over r because it's rolling without slipping. Substitute everything in. You know rotational kinetic energy is just 1/2 I omega squared. So r and r cancel, 2 and 2 cancel, so rotational kinetic energy is 1/5 mv squared. 1/5 plus 1/2, that's 7/10. So potential energy equals to 7/10 of mv squared. From here, you can solve for v. Part 2 for B. Derive an expression for the normal force the track exerts on the sphere at point A. So at point A, the normal force is the one provide centripetal force. There's no other force provide centripetal force. So in this case, normal force equals to centripetal force equals to mv squared over r. We already know what v is, so substitute what you know for v and simplify it. And that's what you have for normal force. Part C. Calculate the ratio of rotational kinetic energy to the translational kinetic energy of the sphere at point A. So rotational is 1/2 I omega squared. Translational is 1/2 mv squared. Again, we know I is 2/5 mr squared, omega equals v over r. So we do a ratio 1/2 I omega squared divided by 1/2 mv squared. As you can see, 2 and 2 cancel, r and r cancel, so it becomes 1/5 over 1/2. Or 1/2 and 1/2 cancel, it's just 2/5. Part D. The minimum release height necessary for the sphere to travel around the loop and not lose contact with the loop at point B is h minimum. the sphere is replaced with a hoop of the same mass and radius. So what's the difference between hoop and sphere? Think about it. Will the value of the H minimum increase, decrease, or stay the same? Justify your answer. The difference between hoop and sphere is that a hoop has bigger moment of inertia. Because its moment of inertia is bigger, it will require more energy to rotate it. Therefore, it will have less translational kinetic energy. That means your V will be smaller. Now, to maintain the V, H, the minimum, has to be bigger. So since the hoop has greater moment of inertia than the sphere, it will require more energy to rotate it. Less energy will be available for translational motion, so its velocity will be smaller. To achieve the same speed at point B as a sphere for a hoop, the hoop will need a higher value of H minimum so it can stay in contact with the loop at point P, so H minimum must be increased. Last question. The sphere is again released from a known height h and eventually leaves the track at point C, which is a height r above the bottom of the loop, so same height as A. The track makes an angle theta above the horizontal at point C. Express your answers in part E in terms of m, little r, h, r, big R, theta, and the physical constants as appropriate. Calculate the maximum height above the bottom of the loop that the sphere will reach. So from after it leaves the C, it becomes a projectile. So you're asked to calculate the height, total height on the bottom. So this total height actually is the radius of R plus your Y maximum. The Y maximum we can figure out from kinematics because we know the velocity at C and we know the angle, so we know initial vertical velocity. We know at the highest point about vertical velocity is 0. We also know during this transition, the acceleration is negative g. So whenever we know 3, we can figure out the rest. Once you find Y max, you simply add R to find H max. So H max again equals R plus Y max. What do we know? We know initial velocity is velocity at C times sine theta. That is a vertical velocity. We know final vertical velocity equals 0. We know vertical acceleration is negative g. To find the Y max, we put in the timeless equation. Y max happens when VFY equals 0, so Y max equals negative VIY squared divided by 2AY. What is VIY? VC times sine theta. What is VC? VC is the same as VA. We know VA squared equals negative 10 over 7G times H minus R. Remember your times sine theta, the whole thing has to be squared, divided by 2 times negative g. G and g cancel. You can simplify Y max. That is just the height above R. To find the total height, you have to add R. So that is the total height. I hope it helps. Thanks for watching. See you next time.